My name is Josh Hulse. This is Team 16, RF Interrogator. It senses changes in the capacitance of a remote sensor. This is an update from the last video. Currently, the ramp generator final PCB is being fabricated as we speak, and the prototype board that we have has been fixed with the proper level shifters to get the correct voltages. Now we have Brandon, who's going to discuss the rest of the transmitter. Then we'll have Jonah, Daniel, and Seth.
So from the fixed proto board, we've been able to use that and test our full transmitters. So using our LNA and our VCO along with the RAM generator to plug into a spectrum analyzer. From this, with our spectrum analyzer, we have just a dipole antenna attached to the spectrum analyzer, so we can send out our RAM generator signal through the whole transmitter chain, and then we can receive it on the spectrum analyzer. And next we will have Jonah talking about the receiver.
Hi, I'm Jonah. I'm going to be talking about the receiver portion of the project. So we discovered oscillations in the receiver board, and we tried terminating these oscillations by putting terminating loads on each of the ends, which preemptively solved the problem. We also validated that the envelope detector of the board was correctly functioning with an amplitude modulated RF signal at 5.8 gigahertz, which produced an analog output with peaks, and verified that the LNAs on the board were amplifying, but there are still issues in the potential oscillations in the bias network due to the high backwards gain, and there are future plans to resolve this by creating a harmonic balance simulation in ADS to analyze the stability. And now I'm going to be passing it on to Seth to talk about the DSP portion.
Hi everyone, I'm Seth Dunbar. I'm an online student in Washington, D.C. I'm going to be talking about the DSP subsystem. So to quickly recap, the DSP subsystem's purpose is to digitize the envelope signal we get from the receiver board, find the peak of that signal, and use that information to calculate the resonant frequency of the target. So some of the progress we've made this semester is we have simulated the effect that different sampling rates will have on our ability to accurately detect the peak. And we've settled on a Texas Instruments DSP chip with 12.5 million samples per second sampling rate. We have developed a peak finding algorithm in MATLAB that has good performance. We're building a test bench so we can send signals to the TI chip to test out how it works. We are also working on programming the TI board with the algorithms, and we're having some difficulty due to some design flaws in the board, so we're going to have to make some modifications to that board in order to get it to work. Next up, I'm going to have Daniel, and he's going to talk to you about some more plans we have for the next semester. Thank you.
Hi, I'm Daniel, and I'm going to be concluding our video talking about some of our plans for the future. So the transmitter is on track to be built by the end of January, and then we'll go into a series of tests on that. Now, as Jonah mentioned, there are some more simulations and tests that we'd like to run with the receiver, but that should also be complete by the end of January. The long lead item right now is the DSP subsystem. Now we have most of the kinks worked out in development for the TI board, so we're targeting having that programmed and tested by March. There are also some connectors that we still need to solder to that board in order to receive the clock signal from the transmitter. Now following that, we can start integrating the system and testing it as a whole. And that should be complete by about mid-April. From there, most of the work will be documentation and getting everything buttoned up in time for the final demo. Okay, so that concludes our video. Thank you very much for watching.